To round off talks on the SciPy library, we'll finish up with the SciPy.Special module. What this does is this, uh, it provides advanced mathematical special functions used in scientific computing, physics, engineering, statistics, machine learning, signal processing, numerical analysis. It contains optimized and numerically stable implementations of many mathematical functions that appear repeatedly in science and engineering. So in mathematics, we have some functions that are called special functions, and one that readily comes to mind would be something like beta function. Then you have gamma function. In fact, they also carry over into statistics where you have beta distribution, gamma distribution, and all of these things. Then you have Airy functions. You have the error function, which it has something to do with the Gaussian distribution and things like that. So, uh, how do you import the libraries? I mean, just you can also, import this for the other ones, right? We begin by importing the required Python libraries. That's NumPy for numerical operations, Matplotlib for data for visualization, and SciPy special for special mathematical functions. Of course, we already know that in working with Python, if you're working with a library for the first time that is not an inbuilt library in Python, like the math library, or what if you like can call it a module or time. So the other ones you have to first of all install them using pip install, then the name of the library, and then for to now use them, you now need to import them, right? So in case you need to know more about the nitty-gritty of Python, you want to check my playlist on Python Basics with EJD, Python Basics. So there I went step by step talking about different aspects of Python that might be of interest to you. So overview of SciPy special functions. The SciPy special module contains several categories of functions. So you have the gamma functions, you have the log gamma, that's gamma logarithm of gamma, you have beta functions, and you have the log beta, you have error functions, and you have ERFC. I think we'll see that when we get there. Then Bessel functions, you have JV, Airy functions, you have orthogonal polynomials like Legendre and Hermite. You have hypergeometric functions where you use things like hype2f1. Then you have statistical functions like NDTR and NDTRI. Then you have combinatorics, that's combination and permutation. Interestingly, I think after this playlist, I'll actually do the maths of special functions. I'll do a playlist on special functions, taking these functions one after the other and doing justice to them. In case you need to know these functions, you want to actually, watch out for that playlist on special functions. So let's start off with the gamma function. So the gamma function generalizes the factorial function. So for positive integers now, the gamma of n is simply the same thing as n minus 1 factorial. So gamma 5 is simply 4 factorial. Gamma 11 is 10 factorial and so on. So example, gamma 5 is 4 factorial, which is 24. 4 times 3 times 2 times 1. That's 24. So the gamma function also works for non-integer values. So, um, so imagine first of all, in NumPy, Matplotlib, and special and SciPy the special. So you have to import all of this, assuming you already have them installed. You're not using it for the first time. So after that, now we now need the gamma of 5, which is simply 4 factorial, and that gives us 24, as you can see. Then how do you plot the gamma function? So you have x from 0.1 to 5 in 500 divisions, and you do gamma of x. Y is gamma of x. Then you plot x against y, and then you get this. So it looks like it looks like this a bowl kind of shape like that. You know, that's what gamma function looks like. So you can have gamma function for non-integer values. Like you can look for the gamma of half, for instance. So one important identity is that gamma of half is square root of pi. So, and square root of pi is like 1.773. So that's gamma SP from SciPy now, SP dot gamma 0.5, right? So you get 1.772, blah, blah. Then you have the log gamma function. So for large numbers, the gamma function becomes extremely large. So instead of computing gamma of n directly, we often compute log of gamma of n. So using gamma ln, this improves numerical stability and prevents overflow. I mean, just like we have in data science, right? When you're dealing with very large numbers, it's usually good to scale the numbers or to find some way of standardizing so to avoid to make sure you have a stable system. So um imagine you want to gamma 100 is a big number, for instance, but if you do the log gamma of 100, you get 359.134 like that. So we keep moving. Then with that we are done with beta function, gamma function. Now we come to beta function. So the beta function is defined as b of x comma y equals gamma x. So you see there's a connection between the beta function and the gamma function. So b of x comma y, that's gamma x gamma y over gamma x plus y. So um it is widely used in probability and Bayesian statistics. Like I said earlier, there's a beta distribution, there's a gamma distribution. So to find the to beta 2 comma 3 now, that's 0.08333. Of course, beta 2 comma 3, it's gamma x gamma y over gamma x plus y. So if you want to work that out, so you have since you know that beta x comma y is gamma x. Okay, that's not like what gamma should look like. Gamma x gamma y over gamma x plus y, right? So that means that beta 2 comma 3, that tells us that beta 2 comma 3 will be gamma 2. I wonder why I keep using square root for that. That'll be gamma 2 gamma 3 over gamma 2 plus 3. So that means you have 1 factorial, 3 factorial over, oh, sorry. Well, that's 1 factorial. Well, that's the same thing as gamma 2, gamma 3 over gamma 5. So that means that you have 1 factorial multiplied by 3. That's 1. Okay. 2 minus 1 factorial. Gamma 3 is 3 minus 1 factorial. Gamma 5 is 5 minus 1 factorial. So that's 1 factorial, 2 factorial, all over 4 factorial. So that's 1. 1 factorial is 1 times 2 factorial. 4 factorial is 4 times 3 times 2 factorial. So this can cancel out. So we have 1 over 12. That's beta 2 comma 3. Okay. It will be symmetric to it will be beta 2 comma 3 is beta 3 comma 2. That's 1 over 12. And that's why the answer here is 0.0833, because we know that if I do this now, I want to print, if I want to print 1 divided by 12. So if you print 1 divided by 12, you get 0.0833, just like this one. So that's what the result is. So you have the log of beta function. The logarithm form of the beta function is computed using log b x comma y. This is useful for numerical stability, machine learning, and Bayesian inference. So you want to print beta log beta of 23, that's minus 2.48 on all that, because that's now log of this 1 over 12 now. So we talk about, so we've considered gamma function. We've seen error for a beta function, which is also dependent on the gamma function. It has an association with the beta function. So we then have the error function. So the error function is important in probability, heat transfer, Gaussian integrals, signal processing. The error function is defined as ERF(x), error function of x. So the error function of 1, for instance, is 0.842. If you run that, or maybe let's say error function of 10, what does that give us? That's 1.0. So what about 100? Error function of 100, that is still 1. So no matter how big it gets, I think it's just gonna be 1. Yeah. So that's the how that works. So error function of 1 is 0.84 something something. Can we have error function of 0? I'm just checking it. Oh, it's 0. How about 0.1? Error function of 0.1. Okay, that keeps changing until we get to, okay, let me do error function of 0.11. We have this. So what about error function of 0.5? We have this. How about error function of 0.9? We have this. So what about error function of 5? 0.99. So it's approaching 0.99. How about, let me go back to 3, for instance, and see what happens. Okay, wow, it's moving fast towards 0.99. So until you get to 10, where it is now 1.0, and whatever else happens, 10.1, it's always 1.0. So take it to anything else, it's 1.0 like that. All right, so we have that. Then plotting the error function now. How do you plot the error function? So you declare your x minus 3 to 3, 500 deviations, and you plot x against the error function of x. And that's what you get right here. So it looks like it's a sigmoid function. So, okay, and that's exactly where we get what we're getting. From -1, it's something like this, and then it gets to 1 and saturates. So it saturates and keeps going. So this one is going closer and closer, and at 10, it gets to 1, and then it stays there no matter what else you consider. And I think on the negative side, so it keeps going. I want to suspect that at -10, it also gets to -1 and stays there. So let me check. That's my hypothesis. I believe that's what it should be. So this should be -1. And then anything else you do, it's always -1. So it starts from saturates at -1 on the negative side and on the positive, and saturates at 1 on the positive side. So that's how that goes. Okay, so that's error function of 10 and error function of -10 are like the points where it begins to saturate. Then you have the complementary error function, which is okay, that was what we saw the other time, ERFC. So the error function of x it has a complementary, which is 1 minus the error function itself. So the complementary error function is error function ERFC of x is 1 minus the error function at x. So if you print sp.erfc at 1, that means 1 minus the error function at 1, which is now 0.1572 and all that. Then you have the inverse function. So inverse error function, that is. The inverse error function computes the error function inverse of x. It is commonly used in statistical calculations and Gaussian probability models. So the uh, inverse error function of 0 at 0.5 is 0.4769, all that. Then, of course, so we've seen gamma function, beta function, error function. Now we move to the next one, which are the Bessel functions. Bessel functions appear in wave equations, electromagnetic fields, vibrations, acoustics, cylindrical coordinate systems. The Bessel function of the first kind is denoted by j sub n of x, j sub n of x. So imagine you have x's. You want to do 0 to 20 in 400 divisions, and y is the JV from SP. That's JV is what you use for the Bessel function in that case. And then you plot x comma y. So Bessel function from 0 on 0 comma x like that. And then if you run that, this is what you get. This is Bessel function J naught. So what if it's 1 here now? So that is n is 1. So it changes shape like this. What if j is 2? This is so the see the shift keeps going like that. What if it is 3? You have all this. Or better still, we can do something. Let me do let me stack things up. Let me say this is y1 and that is 0. Okay. And then I just keep duplicating that and okay, let me do y0, right? Let me do y0. And this is now y1, where this is 1. And then let me do like 5. So 3, 4, 5. So that's y2, y3, y4. And then this is 2, 3, 4. And then what I then do here is y0, comma, y1, comma, y2. Can this work though? Uh, Let me see. Yeah, let me just do that and see if it does work. Okay, now this is what is happening. It's actually working. Yeah, that works. Mm, maybe it is better to have them separately. Let me check that first. Y1, where all this will go. Let me see if that works better. Aha, yeah, this is more like what I want to see. So this is y2, y3, y4. Yeah, so okay, I think we're still going to see this later on even. So yeah, so let me take it back to what it was. Just that. So this is y and just only the y naught, okay? Then we have higher order Bessel functions. So we can compute Bessel functions of different orders. So J naught of x, J1 of x, J2 of x, J3 of x, like the one I did previously. So it's exactly what we have here. So we have this is a smart way of actually running that now. So from 0 to 20, same thing. But for any range, for that's 0, 1, 2, 3. So you find plot x. So x now, then SPJVN. So n can now take value from 0 to 3, and then you run all of that. But let me make it the 5 I made it the other time. That's 0 to 4 now. So I just run this, and then you have those shapes. So when n is 0, that's the blue one. When it's 1, we have the orange one. When it's 2, it's green. When it's 3, it's red. So you can see it, they keep coming down step by step like that. So you see the blue is higher, orange, and so the next one, the blue is higher, and it keeps, so it's more like it's descending somewhat. So you have Bessel function of the second kind, which is the y, which is y sub n of x. First kind is j sub n of x, second kind is y sub n of x. So the Bessel function of the second kind is denoted by y sub n of x. So so to do that, you print so y sub 0 of x, now this is y, this is 0, and then you run that. So we can do the same thing for we can like use this code and see what happens. So we just know that instead of JV, we use YV basically. So I'll create this and bring this down here. This is now YV. I hope that works though. And then yeah, I think that's all we need to change. And I do this. Aha. So this one is the range is pretty tiny. This is from 0 to 20. Looks like we need to 0 to 20 may be too large for this. So let me do 0 to 2 and see what happens here. 0 to 2 still looks pretty somewhat. Uh, okay, the values are pretty big. There's something we need to do to the, so maybe we can do PLT dot sim. I'm trying to see great, no, not great true now. I can use log, right? Sim, is this sim now? PLT, is it log? No, I don't think it's log. Like sim log. No. Okay, let me try this log and see what happens. Yeah, because that was so big, so maybe it's important to just see this. Okay, now 10 raised by 0 doesn't work, so maybe let me go back to the 20 again and see if that, aha, okay, it's taking shape gradually now. So maybe I should extend that to say 50 and see what happens. Yeah, so the value here, so this is even the negative side isn't working here. So maybe it's better to start from like 1. Okay. And we have this. Okay. Or even say 0.9. So we can see that one fully. Yeah, something like this. So just keeps going like that. Is the cell function of the second kind. Then we can have modified Bessel functions. So modified Bessel functions are useful in diffusion, equations, and statistical mechanics. So functions include, I mean, some of these special functions, you can find them a lot in mathematical physics. So you have 1 sub n of x and k sub n of x. So you can print SPIV. This is the uh you have functions like in of x and kn of x. So I can repeat the same thing. Okay, all we just need to do is change from YV to say IV and KV. So let me do IV first. So I put this here, and then I just change this to IV and see what happens. Aha, so see how that goes. So maybe log may not be useful here because we don't have the same issue like the other one. Ah, okay. It looks like log log may still be useful. So log brings out the it brings it out better. So we have this. So but then this is I mean need to start from zero now. Zero to say 0 to 20 may be useful here. Right. So something like this is more like it. Yeah, so that is for IV now. So we can do KV. So let me do the same thing for KV and see what that looks like. So just do the make a code space available. So this is now KV, right? KV. So these are modified Bessel, like it said, modified Bessel, and see what that looks like. So it's something of that. Okay, so we have all of that. Then let's come and talk about Airy functions. Airy functions solve differential equations of the form y prime prime minus xy equals 0, and they appear in quantum mechanics, optics, and wave propagation. So imagine you have something from -10 to 5 in 500 divisions. You have AI, AIP, BI, BIP, SP dot area of X. These are the four components or so. And then you plot. So you plot X, comma AI, label AI, X, comma BI, label BI. And then you have this for your Airy function. So I don't know if log is going to make better sense here. So let me just plot dot log this that okay, and then let's see if it makes a bit more sense. Yeah, I mean log makes it a bit more sensible. So you see the AI is going downwards and BI is going upwards. So we have all of that. So you see log can help you see finer details sometimes. So you may want to think about that. So elliptic functions now. Elliptic functions appear in pendulum motion, electromagnetism, conformal mapping. SciPy provides the Jacobian elliptic functions like when you have U 0.5, M 0.2, and do the elliptic and you print and you get your values like that. 0.4759, 0.8794, 0.9770. Then we have orthogonal polynomials. Orthogonal polynomials are fundamental in numerical analysis, approximation theory, quantum mechanics, spectral methods, and SciPy includes Legendre polynomials, Chebyshev polynomials, Hermite polynomials, and Laguerre polynomials. So let's start with Legendre. Legendre polynomials are commonly denoted by P sub n of x. So P3 is sp.legendre, and you print that. And these are polynomials now. So P3 in this case is 2.5x cubed minus 1.5x. That's that. And then you can plot it, right? You can plot any polynomial. Did I already run this? Yes, so run this, and then we plot it right here. So you have Legendre right here. So n from n equals 0 to 4. So at 0, that's just the straight line at 1. At n equals 0, that's at n equals 1, you have the orange, which is like this diagonal line. At n equals 2, you have this green one, which is just this uh what is it called now? It's parabol, parabolic curve. Then n equals 3. So it's like you now have, you have a crest and a trough, and then it keeps breaking up like that. N equals 4 is now this or that one. So weaving through like that. So and then it becomes very artistic as you keep moving. So if I make it to like 10, so we have it. So it's more like things are breaking up so fast like that. So then we have Chebyshev polynomials. Chebyshev polynomials are denoted by T sub n of x. They are important in numerical approximation and interpolation. So T4 is sp dot Chebit 4, print T4. So x 8x raised to power 4 minus 8x raised to power 2 minus 2.2 e raised to power these are as good as 0 of x, but I mean it's still there plus 1. Then you can plot the Chebyshev polynomial, so you can plot that now, and then this is the kind of thing you get. So again, straight line, diagonal, and it's looking a bit close to the Legendre, the other polynomial we talked about, that's the Legendre polynomials, yeah? So this Chebyshev polynomial right here. So let me make this one like 10 too and see what's exactly the difference between the, okay, yeah, I think I see that now. So let me make this one like 10 also and see what happens. Okay, like you have everywhere is full, but here, I think the height keeps dropping or so. So, but here, like everything still touches, everything touches minus one and one. But here, that for legend, that's not really happening. Like it's getting closer and closer to zero, like that. So that's one thing I've seen with those two. Then you have Hermite polynomials. Hermite polynomials are heavily used in quantum mechanics. They are denoted by h sub n of x. So h3 is sp dot Hermite of 3. It prints h3, which is 8x cubed minus 12x. So plotting Hermite polynomials now is what you get. So yeah, it's everything is getting tinier and tinier. So when it gets very big, like maybe when you get to say, okay, let me do log log and even see what happens. Plot log 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 on both axes, log log like this. Let's see what happens because the value on the other axis is so this one helps us to see to see into what's really happening. So with this now I can then increase this to say 10 and we can see more occurrences. Yeah, so we see all this happening. Um, so we want to go to say, let's say minus 10 to 10 and see what happens. Minus 10 to 10. Okay. Yeah, we see all this here. Yeah, of course, we know log won't work for this. Let's say zero, right? Maybe zero makes more sense because log probably, so it doesn't change anything. So see what's happening there. So log helps us to zoom down into it. If you don't want to use the log, you just come out here and comment. Just comment it out there, and then you have the normal thing. But you don't get, it's more like you're not really getting the meat, the gist of what's happening there. So log helps you to X-ray into to see the fine details of what's happening. So I think log works better still. So you have this whole thing happening right there. So for the Hermite polynomials, then we have Laguerre polynomials. Laguerre polynomials are used in quantum mechanics and radial wave equations, where L3 is sp dot Laguerre of 3. And when you print L3, you have minus 0.1667 x cubed plus 1.5 x squared minus 3x plus 1. So, and then we have hypergeometric functions. We may not want to plot this too. So that's Laguerre. Let's see what Laguerre looks like, right? So I bring this over and just change it to Laguerre. That's all. So, okay, I've done this twice. So I just delete. Okay, I'm bringing it for Laguerre, so I shouldn't copy there. Laguerre. So we need to visualize that. Yeah, so for Laguerre now, so instead of Hermit, we now have Laguerre here. Laguerre. So this is what Laguerre polynomial looks like. Maybe we don't need log here. Let's see. Let me comment out log and see what happens. Maybe we can get some we can still get the idea. So I mean this whole log thing is it's useful when you need to know more about what's really happening. So let's see if I do 5, maybe we get a clearer picture of what's going on. Okay, something like this. Yeah. So N straight line, N1 is coming down, N2 is green, it goes up, N3 red comes down, N4 so it comes this way. So that's Laguerre. Then hypergeometric functions. Hypergeometric functions are among the most general classes of special functions. Many other special functions are derived from hypergeometric functions. So you have hypergeometric 2f1 of 1, 2, 3, 0.5. So you get 1.54, 5177, and all the rest. Then you have exponential integrals. Exponential integrals appear in heat conduction, radiation physics, engineering, mathematics, such that you have exponential integral of 1 is now 1.8951. So it's more like, yeah, You have that 1.8951. Then you have generalized exponential integral where you have EXPN 21. So you have 0.1484 like that. When you run all of that, I've not been running these codes in recent times, but I think we're good. Yeah, so they don't change. So yeah, we then have statistical special functions. Many probability distributions rely on special functions. So you have NDTR, for instance, of 1.96 to be 0.9750. Then you have inverse normal distribution function. So that's oh yeah, NDTR is normal distribution, I believe. NDTR, normal distribution. So inverse normal distribution, that's NDTR, right? The inverse normal cumulative distribution function computes statistical quantiles. So if doing that for 0.975 is 1.9599 and all of that. Then you have combinations and permutations. So SciPy provides combination functions such as n combination R and n permutation R. Maybe I'm going to do a playlist on permutation and combination later if necessary. So you have 5 combination 2 and 5 permutation 2. So 5 combination 2 is 10, 5 combination 2, 5 permutation 2 is 20. Of course, in maths, this is the kind of thing we're talking about. When you talk about permutation and combination, permutation. Okay, let's even start with permutation, right? Permutation simply talks about arrangement, talks about arrangement. Okay. So if I say if I say 5 permutation 2, okay? 5 permutation 2 means in how many ways can two things be arranged out of 5? Okay. So and generally speaking, n permutation r is equal to n factorial over n minus r factorial. That's what that is about. So n factorial all over n minus r factorial. So that when I now have 5 permutation 2, 5 permutation 2 is 5 factorial all over 5 minus 2 factorial. That's 5 factorial all over 3 factorial, which is equal to 5 times 4 times 3 factorial all over 3 factorial. So we stop here because this can cancel out. And 5 permutation 2 is 20. Okay, that's how that works. On the other hand, when we talk about, like I said already, permutation talks about arrangement. Then combination, combination so 5 permutation two means is how many ways can you arrange two things out of 5, right? So combination says in how many ways can you select a number of things out of the total. So combination talks about selection, and that's n combination r, which is n factorial all over n factorial all over uh r factorial n minus r factorial. So the difference is that up here, there's no r factorial down here. Okay, that's the difference. But for combination, there's r factorial in addition to the r n minus r factorial that was there, such that if you now have to do 5 combination 2, means in how many ways can you select two things out of 5? So that's 5 factorial all over 2 factorial into 5 minus 2 factorial. So that is 5 factorial all over 2 factorial, 3 factorial. So like that's then the same as 5 times 4 times 3 factorial because we have 3 factorial down there. And then 2 factorial is 2 times 1 times 3 factorial here. So this cancels out. So we then have 20 all over 2, which is 10. So you can select two things out of 5 in 10 different ways like that. And of course, we can actually demonstrate all these things. Like, I don't know if I should go into that. That's going to be a lot. Well, I feel like demonstrating that, like, you have A, B, C, D, E. In how many ways can you select two things out of 5? So that says you can have A, B, you can have A, C, you can have A, D, you can have A, E. I mean, divided by 2 is taking care of duplication because if you don't pay attention to order, it becomes permutation. So we can have AB. If it was arrangement, AB is different from BA. But for selection, so you just want to select. So if you select A first or B first, it doesn't matter. So AB and AC are the same. I mean, AB and BA are the same. That's why you have the division by 2 for combination. So starting with that, right? So AB, AC, AD. So you can also have uh, Okay, let me not overlap. So you can also have BC, you can have BD, then you can have BE. So what else can we have? You can have so we started with A, we started with B, and BC is CB, BD is DB, BE is EB. That's why we divided by two. Then if you start with C, then you can have C, you can have CD, CD, you can have CE. Okay. You can have CD, you can have CE. Then you can also have uh DE. Finally, you can have DE, DE. So if you count everything, what do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can select two things out of five in 10 different ways. The division by two is because you are removing order. Okay. So but for to select to arrange two things out of five, right? So it will now double. That's why that was 20. That's why that was 20 up there. So it will now double because in this case now, in that case, A, B, and B are not the same. So you have to count A, B, B, A, B, C, C, B. That's why it becomes double for permutation. Okay, so that's what we have for that. That's why we have 10 and 20. So you talk about relative entropy. Relative entropy is important in information theory, machine learning, and uh, common KL divergence. I think I've talked about this somewhere before. So P is 0.4, 0.6, Q is 0.5, 0.5. So if you print the relative entropy, you get minus 0.08. You know, entropy talks about the level of disorderliness of a system. And I remember in information theory, you have this Shannon index, which is a very powerful contribution by Shannon to the field of information theory. Then you have the softmax function. The softmax function converts values into probabilities. It is heavily used in neural networks and classification models. So, that's like deep learning now. So you have x, np dot array 1, 2, 3, then print sp softmax x. So you then have these values now. So this 1, 2, 3 are converted into probabilities. Then you have log softmax. The logarithm of softmax function improves numerical stability. So if you want to improve numerical stability, especially if you are working with large data sets or values that are very wide apart, so taking log is a very nice way of shrinking the system to make sure that there's stability. So talking about numerical stability, right? So in this case, we've talked about sp dot log. So that's from SciPy of log softmax of x. So and you have and the x is all the 1, 2, 3 declared here. So and you have these values. So then we talk about see all of them the way they are you know. So I guess I didn't run this first. That's why we have that plenty stuff. So now it takes goes back to what it should really be. The numerical stability. Special functions often involve large exponentials, large factorials, very small probabilities. So special functions involve very large numbers. That was why I had to use log to be able to see what's really happening for some of the functions, especially some of the polynomials. And they have very small probability. So direct computation may overflow or lose precision. So SciPy provides numerically stable implementations for these situations, like the log sum expo of like 1000, 1001, and all this ends up giving us this value. Then we have vectorization. SciPy functions are vectorized. This means they operate efficiently on entire arrays rather than requiring loops. So instead of having to use loops, they're already vectorized. So if you take x from 0 to 5 in 10,000 divisions, and you get the error function of x in that regard and print, so you have your values like this, all these values. Then in summary, the SciPy special module provides high-performance mathematical functions, numerically stable algorithms, scientific computing utilities, statistical special functions, orthogonal polynomials, wave and diffusion equation tools, and major topics we've covered include things like gamma functions, beta functions, error functions, Bessel functions, Airy functions, and orthogonal polynomials, hypergeometric functions, statistical utilities, and numerical stability using things involving log and all that. Mastering this module is essential for advanced scientific computing in Python. Okay, so you have practice problems. Compute gamma 7, of course, we know that's 6 factorial, which will be 720. Yeah, 6 factorial should be 720. 25 times 4. No, 6 factorial should be Yeah, I think it's 720, yeah. Because 4 factorial is 24. 5 factorial is 24 times 5, which is 120. 120 times 6, yeah. That's gamma 7. Then verify numerically that gamma n equals n minus 1 factorial. So watch out for the playlist on special functions that will help you uh, get correctly into this. Then we have that's that. So I'm going to prove that when we get to deal with it mathematically. Then compute gamma of half and verify that it equals root pi. So I'm going to show all of that. Then log gamma to compute, use log gamma to compute log gamma of 100. Why is it more stable? Why is this more stable than directly computing gamma 100? I mean, when the numbers get too large, it can become probable, unstable. Then we have compute the beta function, beta 3, comma 4. That's gamma 3, gamma 4 over gamma 7. So that's easy to compute even manually. Verify numerically that this happens. That beta x comma y is this. Then, so I think the maths will make that clearer. Then you have compute the error function of 1.5. So using SPERF, then problem A, verify that ERFC is 1 minus ERFC x. ERCFC of x for x equals 2. So you want to show that ERFC of 2 is the same thing as 1 minus ERF of 2. Then problem 9, using the inverse of error function to use the inverse of error function to compute inv of 0.7. Then problem 10, plot the Bessel function J naught of x for x line between from x from 0 to 20, then plot the Bessel function this on the same graph. We've done that a couple of times, so you want to do that. Compute the modified Bessel functions I naught of 2 and k naught of 2. Then generate the Legendre polynomial p sub 5 of x using sp.legendre. Compute the Legendre polynomials p naught of x, p1 of x, and so on and so forth from x equals minus 1 to 1. Then 15, 16, generate the Chebyshev polynomial t4 of x. I think we did that. You want to do it again. Generate the Hermite polynomial h sub 3 of x. Then um, generate the Laguerre polynomial L4 of x using sp.Laguerre. Compute the hypergeometric function 2f1, 1, 2, 3. So when we get to special functions, I'm going to talk about all this very well. Then compute the cumulative probability of z less than or equal to 1.96 using normal distribution, which we saw the other time. Then problem 20, compute the softmax probabilities of 246 using sp the softmax of x. All right, so with this, we come to the end of this interesting video talking about the SciPy special module, talking about special functions in mathematics. And that also brings us to the end of the SciPy library videos. So we have one more library to go, which is the SciPy. And then once we're done with SciPy, we're done with the um, scientific computing with Python playlist, which I started like 2 years ago, and I'm just continuing that now. So after doing SciPy, I think we have like 5 videos or so on SciPy. I'm not sure. Yeah, something like that. And then we move on to special functions where I talk about some of the things we've considered here. Like we see all the theory behind them, how some of the relationships are derived, and so on and so forth. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, the question is, what exactly are you waiting for? Why not go ahead, subscribe, and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first before others and seeing some videos exclusively because you're a member of the channel. You could also request for PDF copies of my notes with which I teach different topics. Then we can also hang out online or physical if you're in the same geographical location at any point in time to discuss whatever interests you on my channel, be it mathematics, data analysis, data science, machine learning, writing books, scholarships, whatever interests you on my channel. There's something for you, definitely. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right, keep doing Python right, keep doing scientific computing right, keep doing data science or anything you find interesting on my channel, do them right. So watch out for the SciPy videos starting from the next video. Bye.